Hello everyone, my name is Adriano and I'm a PhD candidate at the University of Mons. Today it's my great pleasure to present my recent work called Enhanced Wasserstein Distributionally Robust OPF with Dependent Structure and Support Information. This work has been carried out together with Jalal Kazempour from Technical University of Denmark, Zachary de Greve, Jean-François Toubeau and François Vallée from the Power Systems and Market Research Group at University of Mons. Let's begin with the contextualization of our work. We are currently facing an energy transition towards renewable-based systems, but renewable-based energy generation is usually uncertain and variable. It also has space-time dependencies. In the meantime, the energy and resource dispatch has to ensure the reliability and cost efficiency of the schedule for the next day under this uncertainty. But this kind of problem is commonly solved as a deterministic problem, meaning that we only account for a single point forecast of uncertainty. Recently, distributionally robust optimization has emerged as a new paradigm for modeling the uncertainty, and we focused on that particular method. What is DRO in a nutshell? DRO considers the ambiguity. Usually, we define the risk as the exposure to uncertainty, which we model using distribution functions. In DRO, we consider the ambiguity, which is the exposure to uncertainty in this distribution function itself. So DRO asks the questions, how confident are you about the distribution function itself? And to hedge against ambiguity, DRO uses an ambiguity set, which is a family of potential distributions. There are two main types of ambiguity sets, which are the moment-based one, which collects the distribution with same mean and covariance matrix, and the metric-based one, which collects the distribution in the neighborhood of a forecasted probability distribution. There are two main ways of including distributionally robust optimization within a problem. The first one is the worst-case expectation, which appears in the objective function. The idea is to optimize your decision X in expectation for the worst-case distribution Q, which is collected within the ambiguity set A. The other way is to use distributionally robust chance constraints, which means that you will ensure your operational constraints with a high probability for all the probability distribution within the ambiguity set A. As you may understand, the ambiguity set is the main and most important compound in distributionally robust optimization. The more it will include distributions, the more your decision will be ambiguity averse or conservative. That's why we ask a question how to build a fair ambiguity set that is selective enough which excludes unrealistic representation of uncertainty, because you don't want your decision to be optimized for unrealistic distributions. And our idea is to include as much information as we can in the definition of the ambiguity set. And this idea is currently being explored in the literature, where several authors already contributed to include the dependent structure information, the unimodality information, and support information, for example. In this work, we have included both the dependent structure and the support information, resulting in an SDP formulation for the worst-case expectation problem, and using an ambiguity set which is at the frontier between metric-based and moment-based ones. So let's see what it implies mathematically. We have the most common type of ambiguity set, which is the metric-based one, which collects the distribution Q, which are close to Q hat n in the sense of a probability metric, which we use here as the Wasserstein probability metric. The parameter rho is called the Wasserstein radius and limits the distance between Q hat n and the distribution Q inside the ambiguity set. You can see that as a ball in the space of distribution functions. Now let's add a supplementary constraint, which impose the value of the covariance matrix of the distribution inside the ambiguity set. The covariance matrix sigma can be computed as the empirical covariance matrix based on empirical data. In this paper, we had an additional constraint on support information where we imposed that the distribution Q should have realization only inside the support of uncertainty U with probability equal to 1. By doing so, we restrict the probability distribution to take only realistic values of uncertainty. Our main result is the following one. We have reformulated the worst-case expectation problem using the most selective ambiguity set A3 for a linear cost function. We have derived a tractable semi-definite reformulation of this worst-case expectation problem, which is given here, and you will find all details within the paper. Note that matrix M is used for the definition of the ellipsoidal support of uncertainty. Now that we have this main result, we want to apply it to a distributionally robust optimal power flow problem. And as you may know, this problem has a minimax structure with probability constraints, and as such, it requires reformulations. First, we cast the probability constraints into CVAR constraints using CVAR approximation. And these constraints now include worst-case expectation problems within their reformulation. So in the end, we have worst-case expectation problem in the objective function and plural worst-case expectation problem if within the constraints. We reformulate all of them using our theorem, so our main results that we have shown before. And finally, using standard optimization tricks, we end up in a semi-definite problem that we solve using Mosaic and Julia programming. Our numerical study is based on the 24 nodes IEEE reliability test system, and we use two different types of input dataset. The first one exhibits no dependent structure, while the second one has a dependent structure. Here are the results. First, about the computational times, we have observed that they increase as the number of in-sample scenario increase. But we have also observed that the addition of the support information has a limited impact on the increase of computational times. Regarding the out-of-sample analysis with respect to the total operational cost, we have observed that ambiguity set A3 allows to reach the lowest out-of-sample total operational cost for all values of rho. This is due first to the added information about dependent structure, and then to the added information due to support information. For high values of rho, this allows to reach realistic values and realistic distribution function and optimize the decision with a lower total operational cost. In the end, we have also observed that the set A3 performs better for both the independent dataset and the dependent one. This means that the dependence constraints on the added constraints on dependent structure allows to capture any types of dependent structure among the random variables. As a conclusion, we have proposed an enhanced ambiguity set accounting for both the dependent structure and the support information, and we have shown the superior performance of this proposed modeling approach compared to other types of ambiguity sets. Future work will aim at embedding nonlinear dependent structure described by Coppola, or to apply these types of reformulation to real-world application. Thanks for watching, and I'll be glad to answer your questions.